In this video, we continue our discussion on covalent bonding and more advanced concepts. In this video, we're going to look at modes of orbital overlap and the types of covalent bonds, specifically looking at sigma and pi bonds, like we discussed in the previous video. This is the sum up from our last video. We know how to take our VS-EPR electron group arrangements and convert them into appropriate hybrid orbitals for bonding along the correct axes. So we now have a sequence of events to take a simple molecular formula, create a Lewis structure, then we convert the Lewis structure into an electron group arrangement. We can also deduce molecular shape from the electron group arrangement. For this chapter, the electron group arrangement leads us into hybrid orbitals. Now, there are significant limitations to the hybridization model. It works well for many systems, but hybridization is not always consistent with the observed molecular shapes and bond angles. So as we said before in our last chapter, VS-EPR leads us to bond angles and not bond lengths. But these bond angles can be particularly an issue for bonding of larger atoms. So here's a molecule, dihydrogen sulfide, or hydrogen sulfide as it's commonly called, H2S. The bond angle in H2S, if we think about this in a simple sense, H2S would be a tetrahedral electron group arrangement. And we might expect the HSH bond angle to be approximately 109.5. It should be a little less than that because of the two lone pairs up above, but the bond angle in H2S is closer to the angle between unhybridized p orbitals. Also, in general, d orbitals don't hybridize very effectively with s and p orbitals because of the large energy difference. S and p orbitals are much lower in energy and more stable. But the model, while it does have significant limitations, does lead to some good predictions with respect to electronic structure and helps to give us some insight into what the electronic structure for various shaped molecules will be. We discussed types of covalent bonds in our last video, and we discussed sigma bonds. A sigma bond is formed by the end-to-end overlap of orbitals. And that end-to-end overlap, of course, will give us that radial symmetry property, or that circular symmetry about the bond. All single bonds are sigma bonds. Pi bonds are formed by side-to-side overlap, or sideways overlap of orbitals. Therefore, there'll be an overlap above and below the bond. So directly along that bond axis, there's very minimal interaction. But the interaction is in the plane above and below the bond. A pi bond is generally weaker than a sigma bond because sideways overlap is less effective than end-to-end overlap, so the overlap region is smaller. In general, a double bond consists of one sigma bond and one pi bond. You never have two sigma bonds in the same system. The electrons cannot occupy that same region. You can't have four electrons occupying that same location. Only two electrons, one spin up and one spin down, can interact. So the double bond will have one sigma bond, which is the primary stronger bond, and then the pi bond, which is weaker. So we can see here the molecule ethane, C2H6. We can look at the carbon-carbon bond interaction. We know that in C2H6, each carbon has a tetrahedral electron group arrangement. Therefore, both carbon atoms are sp3 hybridized, and they form sigma bonds with the hydrogen atoms by the overlap between the hydrogen 1s and the carbon sp3 orbitals. The carbon-carbon bond, which is a single bond, and it's a sigma bond, is formed by end-to-end overlap of the sp3 orbitals from each carbon atom. So the sigma bond is cylindrically or radially symmetric with its highest electron density along the bond axis. So if you look down the carbon-carbon bond, you see the largest interaction is at the center of that bond. And here's an electron density map for ethane, which was calculated. And there's a relatively even distribution of electron density over all the sigma bonds. Now let's look at another molecule, C2H4. This is ethylene. Ethylene has a double bond, and you can see the valence bond representation of ethylene, C2H4, in the lower right-hand corner. You can see each carbon has two singly bonded hydrogen atoms. The bonds are drawn that way to imply symmetry. One carbon-hydrogen interaction is into the plane of your computer, and the other carbon-hydrogen interaction is pointed out away from the computer. And then the carbon-carbon bond is a double bond, and it's in the plane of your screen. The carbon-carbon double bond then tells us that we have to have one sigma and one pi interaction. If we think about ethylene, C2H4, what is the electron group arrangement around each carbon? It's the same for both carbons. If you look, there are 3 electron groups, 2 single bonds and 1 double bond. Therefore, since there's 3 electron groups, it is a trigonal planar structure. And indeed, ethylene is a planar molecule, but that trigonal planar structure then tells us that we need 3 hybrid orbitals. 3 hybrid orbitals will be sp2. So we have 3 sp2 hybrid orbitals. Each of the 3 sp2 hybrid orbitals is involved in a single bond. One to a carbon-hydrogen, another to a carbon-hydrogen, and a third to the carbon-carbon single bond. That accounts for 3 of the 4 bonds around carbon. Carbon always has 4 bonds to it. And so 3 of those are single bonds, 2 carbon-hydrogens, 1 carbon-carbon. The fourth bond comes between the carbon and the other carbon atom, and that's from the unhybridized 2p orbitals. The unhybridized 2p orbitals are half filled, and they have a side-on interaction. We'll generate molecular orbital diagrams for these types of systems in our mechanics videos. Now let's look at the molecule of what's called ethine or acetylene. That's C2H2. The valence bond, or the Lewis dot structure for this molecule, is shown in the lower right-hand corner. Each carbon has 1 hydrogen attached to it, and then each carbon is bonded to the other carbon via a triple bond. So in this case, what is the electron group arrangement around carbon? It is a linear electron group arrangement because there are 2 electron groups, 1 single bond and 1 triple bond. So this is a linear electron group arrangement. Therefore, we have 2 electron groups and we need to have 2 orbitals. We will have an sp hybridization. The sp orbitals are half-filled for each carbon atom, and one of those half-filled orbitals will interact with the hydrogen atom, 1s orbital, to form a sigma bond, and the other sp orbital will interact with the other carbon atom, end-on, to form the single bond. So in this triple bond, there's 1 single bond, and that is or 1 sigma bond, excuse me. And then there are 2 pi bonds. And the 2 pi bonds come from the 2 unhybridized p orbitals on the carbon atoms. Those 2p half-filled 2p unhybridized orbitals interact, forming the side-on pi interactions. And they're on two different axes. We can see here, these are electron density maps. We saw things similar to this back in chapter 9, where we were looking at covalent bond interactions. So you can see that on the left-hand side is a topographic map. We see the two carbon atoms as the dots in the center of the map. And the map itself shows electron density. Electron density is highest at the carbon atoms and next highest between the two carbon atoms, where the bond is occurring. For a carbon-carbon double bond, we see there's more electron density between the two nuclei than there is in the carbon-carbon single bond. And for the carbon-carbon triple bond in acetylene, there's even a higher electron density between the two nuclei. That tells us that the double bond is stronger than the single bond, and the triple bond is stronger than the double bond. However, a double bond is less than twice as strong as a single bond because the pi bond is weaker than the sigma bond. But in terms of bond order, a single bond has a bond order of 1, a double bond has a bond order of 2, and a triple bond has a bond order of 3. So bond order relates to bond strength, but it is not directly proportional. Now we consider an interesting case of two molecules of what are called dichloroethylene. So this molecule is C2H2Cl2. Each molecule has one carbon-carbon bond, two carbon-hydrogen bonds, and two carbon-chlorine bonds. And each carbon atom in both molecules has one carbon-carbon bond, one carbon-hydrogen bond, and one carbon-chlorine bond. But the two molecules are different, and they don't interconvert. We saw this in the last chapter when we were looking at properties of molecules. And we see that what we call cis 1,2-dichloroethylene, if it's a cis system, the chlorines are on the same side. And then we have trans 1,2-dichloroethylene. That's where the chlorine atoms are on opposite sides. In this case, we have one sigma and one pi bond. If you can break the pi bond, then you just have a sigma bond, and the molecule can rotate around the carbon-carbon bond. And in fact, if you shine this with ultraviolet light on this system, you can get cis and trans 1,2-dichloroethylene to interconvert by temporarily breaking the pi bond. That concludes this video. We'll finish up with concepts in our next video.